Okay. Gonna do some more molecular orbital diagrams today. And then, before we can do one that's more complicated, so what we're doing today is more diatomic molecules. Before I can throw in a third atom, we have to have another conversation about shape. Now, you've already had a conversation about shape. It was called valence shell electron pair repulsion theory. And you learned what it was that dictates shape. We're going to do that and a little bit more. We're going to look at, so oxygen, here's the atomic orbital, here's an atomic orbital, molecular orbital goes in the middle, and that's an oxygen, and this is an oxygen, and this is an O2. Might have to move my diagram a little bit there, because I'm a bit squished. So we'll revisit valence shell electron pair repulsion theory. And when I teach it in general chemistry, I say everything that's a tetrahedron now, you go ahead and call sp3. And we don't really tell you why. We just say, this is what it's also called. When you do organic, it's a tiny bit more information with it about blending of orbitals. We're going to do some more of that. And then we're going to give individual hybrid names to each of those geometries. And then when we know what a geometry is, we can see if the orbitals line up correctly. All right, so oxygen was 1s2, 2s2, 2p, 4, 6 valence electrons, 2 core electrons. All right, so we figured that we didn't need to show a representation of the 1s or the 2s because they were redundant. We already had those covered. That however many number of bonding molecular orbitals you build, you have the same number of anti-bonding molecular orbitals, and they all fill, therefore they cancel each other out. 1, 2, 3, 4, 1, 2, 3, 4, which goes 1, 2, 3, 4, Hund's rule, put them into individual orbitals before you pair them up. Pauli's exclusion principle, if they're in the same orbital, they have to be spin opposed. And then Aufbau, move up to the next energy level. Hund's rule, put them in individual orbits. Now there is something in there that I told you about. There's a selection rule that says which way the electrons spin. And that some spin transitions are allowable and other spin transitions are forbidden. And we might go there. We probably have to at some point. Okay, this bonding molecular orbital is from direct overlap, which makes it a sigma bond, sigma molecular orbital. These are because the symmetries of the p orbitals align. They are pi bonds. And then these are the anti-bonding orbitals, 2 pi stars, and then this is the anti-bonding sigma orbital. So we constructed this last week, and what we didn't do was calculate what the bond order was. How would you calculate what the bond order is?
number of electrons in bonding molecular orbitals minus the number of electrons and number of molecular orbitals.
Number of bonding electrons minus number of antibonding electrons, and because 2 electrons shared between 2 atoms is a bond, you have to divide the whole thing by 2. So how many electrons are in bonding molecular orbitals? These ones. These are your bonding molecular orbitals. And then these, the asterisk, those are your antibonding molecular orbitals. So number of bonding electrons is? 6.
2.
Minus 2 divided by 2 equals
2.
2. So the oxygens in a molecule of dioxygen. Oxygen is just called oxygen unless you're speaking to somebody who works with it. Those people who work with oxygen know that there's slight variations of its form, and we call that one O2 dioxygen. Okay. There's a double bond between those, which is what we knew already, because if you write the Lewis structure actually predicts that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Bond those 2 together. That's a covalent bond, 2 electrons shared between 2 atoms. And then bond those 2 together, 2 electrons shared between atoms. The oxygen on the left now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Oxygen on the right has 1, 2, 3, 4, 5, 6, 7, 8 electrons. That's what our Lewis structure predicted. It's supposed to have 2 bonds between those 2 oxygens. But what the Lewis structure didn't predict was the unpaired electrons that gave us the paramagnetism that we discussed last week. Okay? Which tells us, although that's a nice, handy, shorthand way of making the atoms bond to one another, there is something here in this symbolic math, and all it is just construct the diagram and put the electrons in the right place. This reveals something that wasn't revealed here, which means this has some use. Okay, how would we describe O2? O2 has a covalent bond, so we don't use the word compound. We use the word molecule. Covalent bonds make molecules. Ionic bonds make compounds. So that's a molecule. What kind of molecule is it? How many atoms does it have?
2.
So it's a diatomic molecule. Are those 2 atoms different to one another? Or are they the same? They're both oxygens. They're both the same. So we wrote a molecular orbital diagram for H2. We wrote a molecular orbital diagram for F2. And we wrote a molecular orbital diagram for O2. These are all examples of homonuclear diatomic molecules. Same atom, the same type of atom, 2 of them covalently bonded together. So it's a homonuclear diatomic molecule. Let's do one more, and then we're going to move on to some heteronuclear molecules, because those are slightly different. Here's O2. There's N2. What do they have in common? O2 and N2. Where might one find them?
In the atmosphere.
In the atmosphere. What percentage of the atmosphere is O2?
Not as much as nitrogen.
I know, but how much? What percentage of the atmosphere is oxygen? No more. 21. What percent of the Earth's atmosphere is nitrogen?
$56.
No. No.
62.
Add 21 to 78, what you come up with?
99.
These two gases are 99% of the Earth's atmosphere. What does that tell us about them and their nature?
Very stable.
They are stable. And another word for stable would be unreactive. Everybody thinks that oxygen is reactive. No, it's not. It can't possibly be reactive if 21% of the sky, 1/5 of the sky is oxygen. Cannot be reactive. Yes, it does that one big reaction. Makes things burn. It does that other one big reaction. Makes life exist. But other than that, other than those two things, doesn't do anything. And oxygen it's double bond. Oxygen's in group 6. 8 minus 6 is 2. So oxygen always makes 2 bonds. How many bonds does nitrogen always make?
3.
So if this is 2 nitrogens bonded to each other, how many bonds on the left, how many bonds is this atom on the left looking to make?
3.
How many bonds on the right is this nitrogen looking to make?
3.
Should be a triple bond between these two. And some lone pairs. Okay, here's a nitrogen. Here's our atomic orbital. Here's a molecular orbital in the middle, and an atomic orbital, which is nitrogen. N2 goes in the middle, and nitrogen is 1s2, 2s2, 2p what?
3.
3. Something subtly different happens when you blend nitrogens, and it's because of, it doesn't have to be the same height. It's because of size and a little bit of electronegativity. It's going to be subtly different. Subtly different than oxygen. Now, if you didn't know that it was going to be different than oxygen, it doesn't matter. It's not going to affect our outcome. But because I'm telling you and showing you, you now have to know it. That was our 2p. Here's the 2p's. Let's look at the 2p. When you bring the electrons in the 2p together, have 3 atomic orbitals on the left and 3 atomic orbitals on the right. That's 6 atomic orbitals. And by linear combination of atomic orbitals, that means I need to have 6 molecular orbitals. Here, I have 3 and 3. That's 6 boxes. So I have to have 6 boxes under my new rearranged electrons being shared between the atoms now. This is what the electrons look like when they're on the individual atoms. When I blend them together and share, this is where the electrons go. We saw fluorine. Fluorine looked like that. We saw oxygen. Oxygen looks like this. Between oxygen and nitrogen somewhere, something very, very small happens. The p overlap gets a little bit better. And so the pi orbitals turn out to be just a little bit lower in energy. Remember, energy is going this way. That is not going to stop the sigma star antibonding orbital from being the least stable orbital. It pretty much always is, because its node between the 2 atomic orbitals right there runs right down the middle. So all that's happened is that the pi's have switched places with the sigma. And here's why, if you didn't know, it would not affect your outcome. 1s2, 2s2, 2p3. We've already figured out that we don't need to write the 1s and the 2s down because they're below the electrons that are doing all the interesting stuff. 1, 2, 3. Okay? Those are your atomic orbital energy diagrams. Go put the electrons in the middle. Each box represents a molecular orbital, which represents a bond. And you can have 2 electrons per bond. If you have 2 electrons in an orbital, they must be spinning in opposite directions. How many total electrons are there?
6.
6. So the diagram, tell me what to do. Oh, no. No. Yeah, I know what you're doing. I know what you're saying. But what happens next? Do that one. And then I do this one. And then I do that one. And then I do this one. And then I do that one. Because Hund's rule kicks in. Don't put 2 electrons in the same orbital if you've got an empty orbital somewhere else to put it in. Okay. What's our bond order here?
6 minus 0.
I have 6 electrons in bonding molecular orbitals. I have no electrons in anti-bonding molecular orbitals. All divided by 2 to turn electron count into bond count. 2 electrons per bond. 3. That 3 represents a triple bond. And a triple bond is a sigma bond, direct overlap of those p orbitals, and then a pi bond, and then another pi bond. Triple bond is a sigma plus a pi plus a pi. Got it. All right, so the Lewis structure works. Let's make some heteronuclear diatomic molecules. There was a point. Did I do it in organic or did I do it in inorganic or did I do it in both? Where we wrote the rules for Lewis structures down.
We did it for
always
organic.
Okay.
Miranda, whatever.
Are you sure?
I
I didn't
know.
see if she asked, or she thinks she asked me, but it was.
That's true.
So we know that hydrogen always makes one bond because it's an H with a dot, it's in group 1. And things in group 2 would only make 2 bonds, but because they're metals, metals don't do covalent bonding. Non-metals do covalent bonding. There's nothing really of interest in, except for boron, in group 3. There we go. Group 1. Group 3, boron always makes 3 bonds. And then I get to be group 4, which means that carbon, and now, because we're in inorganic chemistry, silicon, not really going to bother with germanium, might do a little bit of tin, but carbon and silicon always make 4 bonds because they're in group 4. And then group 5. Group 5 is now on the right-hand side of the periodic table. So we have a lone pair of electrons. So our nitrogen and phosphorus always make 3 bonds. So we have a carbon here, I'll show you the difference. There's a carbon. And now here's the nitrogen. That non-bonding pair of electrons gives the nitrogen 5 electrons, but only 3 bonding electrons. Therefore, we anticipate that it's going to have 3 bonds. If you're in group 6, like an oxygen or a sulfur, you should have 2 bonds. 1, 2, 3, 4, 5, 6. 2 non-bonding electrons. It's only the 2 bonding electrons. It's only the bonding electrons that can do the bonding between the atoms. Group 7, things like fluorine and chlorine and bromine and iodine can only ever make 1 bond. Because 1, 2, 3, 4, 5, 6, 7. 6 of those electrons are in non-bonding pairs. That only leaves 1 bonding electron left to do the stuff. All right. So we saw H make a homonuclear diatomic molecule, H2. And we saw F make a homonuclear diatomic molecule, HF. I'm sorry, F2. What if I take this atom that only wants to make 1 bond, and that atom that only wants to make 1 bond, and I put them together? Here we go. Now I'm looking at a heteronuclear diatomic molecule. 2 nonmetals bonded together covalently by sharing of electrons. But those 2 atoms are a different type of atom. So this is a heteronuclear diatomic molecule. Okay. I'll have an atomic orbital on the left, a molecular orbital in the middle, and an atomic orbital on the right. There is a school of thought that says the most electronegative atom goes on the left in these diagrams, but good luck trying to find anybody that still follows that convention, because we always write any of the molecules that you can think of, we always have the second electronegative atom on the right, just the way that it's written. So the diagrams would be backwards and they wouldn't scan and read the same way. Let's have a hydrogen here. That hydrogen is 1s1. We're going to have F here. And this is 1s2, 2s2, 2p5. It's in group 7 of the main one. Watching a quiz show last night, English, and they said, which group 7 atom is added to steel to make blah 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 named steel? English quiz shows are really difficult. Group 7 for us used to mean the halogens, but group 7 is the middle of, oh, this one has got it. It's the middle of the periodic table. The answer was manganese. So, because we're now inorganic chemists, we use the 18 group numbering system. Okay. Those 10 in the D block now count. So what, carbon's in group 4, right? It is. So those of you that are also in organic chemistry, carbon is still in group 4. During this hour, it's in group 14. Here's hydrogens, single s orbital with one lonely electron in it. Here's fluorine. Its 1s electron is all the way down here. The more electronegative your atoms are, the further down the diagram their electrons go. 1s, 2s, you know what, I should probably look it up. I don't know if the 2p is below this 1s or above it. I think it might be above. Because it is a 2 and it is a p. That is, of course, if it's even in the book. I think it probably is. No. No, it's not. Where did I put that eraser? Ooh. It is lower. Okay, so we get the usual progression of 1s, 2s, 2p, but because hydrogen is very, very small, and its electron is incredibly close to the nucleus in comparison with those for fluorine, its energy is all the way up here. Okay, what are we going to do? One S2, 2s2, 2p5. 1s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5. Here's where knowing a little bit about both camps, the nice simple Lewis structure that we learned years ago, and now the new math of molecular orbitals, is going to come in handy. There's the H dot. Here's the F. What role does that electron play in the covalent bond?
It's going to donate itself.
It's going to donate itself and become half of this new bond. And that electron?
It's an accept.
It's going to be the other half of the bond. What role do these two electrons have?
It's like bonding, but not for those two.
Not at all. Those are non-bonding pairs of electrons. They're not going to be part of our scheme. They're not part. They don't do the bond. So, when I look, there's an electron. Here's another electron. That's the atomic orbital that I have to consider, and this is the atomic orbital that I have to consider. And I'm going to blend those two atomic orbitals. How many molecular orbitals are we going to make? Linear combination of atomic orbitals. Molecular orbital is a linear combination of atomic orbitals. If I have this atomic orbital, that atomic orbital, and I add them together, well, I'm not going to say add them. If I blend them into one another, how many molecular orbitals do I make? You always have the same number. Diagram's gone. Go back and look at this diagram. How many atomic orbitals were there? 3 on this side, 3 on that side. How many molecular orbitals were in the middle? 1, 2, 3, 4, 5, 6. You always have the same number of molecular orbitals as you do atomic orbitals. So, one of my molecular orbitals is going to be lower in energy than the individual atomic orbitals. What's it going to be called? The other molecular orbital is going to be higher in energy than the others. What's that one going to be called?
The anti.
That one bonding electron and this one bonding electron go here. The reason why I pulled back a minute ago from saying if I add the orbitals together, if I add them constructively, I get this. If I add them destructively, I get that. And adding them destructively is the same as subtracting the orbitals from each other. Adding and subtracting. Those are my two permutations. So what does the rest of the diagram look like? What do you think happens to these 1s electrons?
Nothing.
Nothing. What do you think happens to those 2s electrons?
Nothing.
They're not going to be this high up. This is not drawn to scale. And now, what do you think happens to those electrons?
Nothing.
The 2py and the 2pz. Nothing at all. Now, this 1s, well, I'll write it in, but we don't have to consider it because these are core electrons, okay? This is my valency. Boom, 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 boom. Let's make that sigma quite clear of where that sigma actually is. All right, describe to me what this molecular orbital diagram is showing me. Only need to talk to me about the valence. What can you see? And it is the same as the Lewis structure. It's the same as the Lewis structure. the Lewis structure predicted this correctly. These two electrons are the new bond. And then this pair of electrons, and that pair of electrons, and that pair of electrons have not changed in energy because they're not part of the bond. They are lone pairs of electrons. This is a lone pair. That is a lone pair. Get it? Okay. Let's do a new and exciting one. The next one looks, when we're building it, like it's going to be more complicated, and then it turns out that it's actually easier. This one has stray electrons, and therefore is difficult to read, but hey, those electrons aren't part of the bond, so they don't change in energy. When you bring electrons together, there has to be a benefit for them to bond. That's why the green loop where the electrons are, there has to be some benefit for making the electrons sit in the bond between those two atoms. If there wasn't a benefit, they wouldn't do it. Okay. Let's do, so if nitrogen and oxygen are 99% of the Earth's atmosphere, what's the other 1% made of? Everything else, right? What's the most abundant next gas?
What does it start with?
A.
Argon.
And how abundant is argon?
I mean, it's no.
That means that any other gas that you may have heard the name of exists only in trace amounts in the atmosphere. Argon is group 18 for us inorganic chemists, group 8 for the general chemists watching at home. Inert, doesn't react with anything.
What about carbon dioxide?
What about carbon dioxide?
Is that just a trace thing?
Got your carbon dioxide right there. Is it the global warming thing? Probably. Probably. Are we causing it? Seems like a legitimate answer. But also, I read recently, well, again, I was watching that English quiz show. There's an English quiz show that I watch. It's called University Challenge. And if you don't know your 13th century Swedish philosophers and quarks, they were up and down quarks on this quiz show last night. It's ridiculous. I can answer maybe like 4% of the questions on this show, and I'm relatively intelligent. I cannot keep pace with these people. I don't know my poets, my philosophers. I don't know which counties border what. They were asking the names of the French prefectures. It's just like, okay, it's It's not Wheel of Fortune. But I learned from watching that show a couple of weeks ago that in medieval times, England had a thriving wine industry. Because it was much warmer in England in medieval times than it is now. Much, much, much warmer. So what did we do between then and now to cool the atmosphere so much? I don't know. I think it just happens. We had an ice age, and then we warmed up, and then it cooled down again, and now it's warming back up again. Are we to blame? I don't know. I don't know. I think that it's probably legitimate that we should not do some of the dumb stuff that we're doing, but I also think that it's kind of egotistical to think that everything happens because of me. It must be me because I'm so important. Don't know. I don't know. I'm open to all arguments. Carbon monoxide. So my atomic orbital goes here, my atomic orbital goes here, and my molecular orbital goes in the middle. And carbon is 1s2, 2s2, 2p2. And oxygen is 1s2, 2s2, 2p4. All right, here's what I want you to do. I would like you to draw the Lewis structure of carbon monoxide now. Take a minute. Draw the Lewis structure of carbon monoxide. Keep it to yourself, and we'll figure out if that fits the description of what we get when we do the molecular orbital diagram, because the molecular orbital model should uphold a rational Lewis structure. Might reveal something that we weren't expecting. And of course, I wouldn't be asking you to do it if it was like super simple. This one's a little taxing. Here's the 2p for carbon. What would the 2p for oxygen look like?
It's electronegative, so maybe lower.
Lower. Carbon is 2p2, and oxygen is 2p4. There's the first three, and then there's the second one. When it comes to MO diagrams, there's no real wrong way to do this, but we do tend to start at the right, at the left, work our way right, and then double up and come back. The reason that we do it that way is that it leaves the unpaired electrons, the bonding electrons, open for you to mix. Okay, somewhere between oxygen and nitrogen, the way that the orbitals mix changes, and we have the pies become a little bit lower in energy than the sigmas. And for carbon monoxide, carbon, so nitrogen in the middle, carbon here and oxygen there. It's not both oxygens. So we're going to take the model that the nitrogen gave us, which is an oxygen and a carbon on either side of the nitrogen. So this MO diagram kind of fits the nitrogen field more than the oxygen one. Now if you did this wrong, guess what the outcome would be? Nothing at all. It would have no consequence at all. If you flip these two the other way, for us, no consequence. If you were working at NASA and this was super important stuff, somebody might, do you work at NASA? You got the hat. You know, somebody might yell at you, you did that wrong. For us, it's just not gonna matter. Okay, how many molecular orbitals should I have? 6, because I had 6 atomic orbitals. I had the 2px, the 2py, and the 2pz that belong to the carbon. I have the 2px, the 2py, and the 2pz that belong to the oxygen. All right. So this is pi and a pi. Here's my sigma. There's my pi star. And then here's my sigma star. Put the electrons in the boxes. One,
And 0.
2,
Pi's efficient.
3,
Pi.
4, 5, 6. What did your Lewis structure of carbon monoxide look like? Did anybody write one? Couldn't make it work, right? Doesn't want to work because carbon's supposed to have 4 bonds and oxygen is supposed to have 2 bonds, and they don't come together right. They don't. How many bonds are between carbon and oxygen in carbon monoxide?
3.
This tells me that carbon monoxide has a triple bond. Where have we seen this before? At least let me think. Looking for a good example. Aluminum's a metal. It's better if I use a non-metal. Here's boron. There's hydrogen. Boron only has 3 electrons. 2 electrons shared between 2 atoms is a covalent bond. So that's borane right there, BH3. I've made all the covalent bonds that I can possibly make. Borane is not stable and doesn't want to exist because it doesn't have 8 valence electrons. If I find, here's a hydrogen. Now here's something that we haven't seen yet in, we saw it a little tiny bit in organic chemistry, but we certainly didn't see it in general chemistry. That's a hydrogen atom, okay? H, dot. It has no charge. if I remove the electron, it goes up to being H+. If I give it another electron, which it's capable of doing, so this would be 1s0, that would be 1s1, and this would be 1s2. Hydrogen, hydronium, hydride. If I introduce Mr. Hydride to Mr. Borane, hydride gives both of its electrons to the boron. Is that a covalent bond? Yeah. Yeah. We've become very, very accustomed to covalent bonds being one electron here and one electron there, shared between two atoms. But the definition of a covalent bond is two electrons shared between two atoms. And as easily as it could be this, it could be that. Two electrons from here, no electrons at all from there. And now, this is a coordinate covalent bond. It used to be called a dative bond. Two electrons between two atoms. To draw the Lewis structure of carbon monoxide, you have to do that. You have to make the carbon and the oxygen bond together. Here's a carbon. Here's an oxygen. If I bond that, the carbon on the right has 5 valence electrons. We do this. Doesn't work. Okay, I've bonded all of the non-bonding electrons that I can, because oxygen only had 2 non-bonding electrons. So what I have to do is allow those 2 to become part of the bond. You have a triple bond between the carbon and the oxygen. That's going to give us something that we really hadn't anticipated, and we're going to use later on. So, 1, 2, 3, 4, 5, 6, 7. Did anybody successfully write the Lewis structure for carbon monoxide? If I bond those bonding electrons together and those bonding electrons together, and then I slide those non-bonding electrons and give them to the carbon, I now have 1, 2, 3, 4, 5, 6 electrons between the carbon and the oxygen. And then these 2 electrons here on the carbon, 2 electrons there on the oxygen. Did not expect you to get that. Later on, in the final third of this semester, we're going to discover that, oh, somebody's reading Molecule of the Week. We're going to discover that carbon donates itself in carbon monoxide to other things through, of all things, the low pair of electrons. What low pair of electrons? It's not supposed to be there, but it is. All right, let's do a little bit more. carbon monoxide is a poison. Have you all heard of it being poisonous? Yeah, should have. It's the result of an incomplete combustion of fossil fuel. So you should never start your car with your garage door down. You should never, you should be very conscious of starting a furnace in the winter if pigeons have made a nest or squirrels have made a nest in your chimney, because unless you have the solid flow of oxygen across the flame, you don't get complete combustion, which makes carbon dioxide. Carbon monoxide is colorless, odorless, tasteless, and bonds through this to the iron in your hemoglobin, in your blood. And it bonds stronger than dioxygen does. What other poisons are out there in nature? Name me another poison.
Another poison? Like just anything? Like poison ivy? What you mean? Or what? I'm so confused.
Name me
Like
give me
a
a
gas.
chemical name of,
Oh.
of a poison that you've heard of by watching, Murder, She Wrote. Cyanide. Do we know what the chemical formula for cyanide is? Curiously, English quiz show, cyano was one of the quiz questions last night on last night's episode. So you've got to know what your cyanide is, and then it led into cytochromes and cytoplasm and all sorts of stuff. Don't know everything much yet. Ide at the end of a word means negative. Should not have to tell you again. Ide means negative. Cyan means blue. Blue. Because cyanides are blue. Sometimes. Here's an atomic orbital. There's molecular orbital. Here's an atomic orbital. There's the carbon. There's the nitrogen. Carbon is 1s2, 2s2, 2p2. Nitrogen is 1s2, 2s2, 2p3. Nitrogen is more electronegative than carbon. And because now we're on carbon and nitrogen end, we're further left on the periodic table. When these orbitals combine, I'm fully anticipating that the pi's are lower than the sigma. bond order in cyanide?
2.
I've written the carbon and the nitrogen, but I never wrote the negative charge down. What does the negative charge represent? An extra electron. Where in my diagram do you think I should start to put it? I think I know that it's going to end up here. But should I put it there or should I put it here? You could make a case either way. Nitrogen is more electronegative. Electronegative atoms should probably have the nitrogen. Should probably have the electron. I have an empty orbital here. Might be nice if I put individual electrons into individual electrons. Individual electrons into individual orbitals. Tendency for people to write it is to put it here. Might not be the best place for it, but nitrogen is the more electronegative atom, so why not? Cyanide has a triple bond. Remember how to write formal charge? I don't know if it's how we want to go back down. Maybe I set this as homework for you. Look at the cyanide and try to predict which of those two atoms is actually carrying the negative charge. Maybe we'll do it. Maybe we'll do it. Because again, that might be something important. All right, so what we have is, here's some cyanide, and here's some carbon monoxide, and here's some nitrogen. And they all had variations on the same molecular orbital diagram. And we wrote it all down just to get to this. New arrow. Cyanide, carbon monoxide, and dinitrogen. Oh, so it's nitrogen for everybody in the world, unless you're a researcher on nitrogen. And I just said that without thinking, because that's what my PhD's in. That's dinitrogen, two nitrogens stuck together. Cyanide, carbon monoxide, and dinitrogen are isoelectronic. They have the same number of electrons. All right. Let's look at this. There's a carbon. There's a nitrogen. Make a bond. Make a bond. Make a bond. How many electrons does the nitrogen have? 8. How many electrons does the carbon have? 7. Guess which one of these atoms is going to pick up the negative charge? That's where the negative is. But because we write Cn minus, the knee-jerk reaction to that is, oh, nitrogen's more negative. It should get the electron. There's your extra electron right there.
Wait, why is it spinning?
Yeah, does that have to be going down? Or should be going up?
Sorry, I didn't hear what you said.
Oh, okay.
Have balloons, because we need balloons to do valence shell electron pair repulsion theory. But if I blow them up now, and I've only got 10 minutes, then they're not going to last until Thursday. So I'm going to postpone valence shell electron pair repulsion theory and naming of the hybrid orbitals. Oh, I'm still looking at the book now. So in the book, they do HF, page 50. They do carbon monoxide, page 50. They do ICL, that's an interhalogen of iodine and chlorine. They do some unnamed molecule elsewhere. They don't appear to really do the switch that I showed you between the pi and this. Oh, they do, page 47. Oh, this is a fairly good book. They also, things that we did last week on page 46, have little balloon pictures of S's and S's overlapping to make a sigma bond. S's and P's overlapping to make a sigma bond, and P's and P's overlapping to make a sigma bond. Alright. So, as a bit of a precursor, Thursday, I'm going to break out something called the symmetry table, and we're going to look at shapes of molecules and what happens if I rotate them or reflect them, and how many times do I have to rotate them, and how many degrees do I have to rotate them before I get the same image back. It'll make sense when we do it. So immediately before we launched into molecular orbitals, we had a quick discussion about Linus Pauling's valence bond theory and said, it's good, it's quick, it works, it gives us a notation that we're going to use, but it failed to predict that oxygen was magnetic, paramagnetic, and therefore it has been superseded. However, there are things that we are going to continue to use. You're really going to call it coordination number? Because that's not true. Okay, I'm not going to. We're going to talk about coordination number, but I'm going to do it after the fact. I'm not going to put it on this table. A to B, all right? You're going to have a hard time making that be anything other than linear. So here's just the classification. This is the name of the geometry. And then here's the hybrid orbital that describes it. And we said, and we know this from organic chemistry, alkynes are sp, they are linear. And that if I had three things around, and that would be a trigonal planar, and that would be sp2. And then if I had 4 bonds, around a central atom, that would be tetrahedral. And we would call that sp3. I'm also now going to start to introduce a little bit of a symmetry label we call tetrahedral TD. Now, this is an atom that is bonded, B becomes a bond. So my chemical formula is AB or AB3 or AB4. Some texts write a lone pair of electrons in as L, and some texts write it in as U. Not sure if we're even here yet. No, not quite. So L gets to be the lone pair, and so now I have this. You should know what that is. That is a trigonal pyramid. And trigonal pyramids are based on a tetrahedron. So technically we haven't done anything strange here. What also is based on a tetrahedron is the situation when you have 2 lone pairs of electrons around a 4 potentially bonded object. So 4 areas of electron density, 4 areas of electron density, 4 areas of electron density. These are all bonds. This is 3 bonds and a lone pair. This is 2 bonds and 2 lone pairs, and that gets to be bent. They're all based on the tetrahedron. They're just mutations of. If that angle is 109.4, then this angle would be a bit more. Tends not to be that much more. This angle here could be squeezed down to like 108, 106. And then that angle would be squeezed down to less. So these are always squeezed down. We can look those numbers up, it's not important. Okay. All right, so that's the very, very basics that we learned in general chemistry. We're going to add a 5th area and a 6th area of electron density, and we're going to make square pyramids, square planar materials, trigonal bipyramids, and seesaws. And then we're going to give them the possible, because now I'm not dealing only with carbon, I'm going to be dealing with metals. We're going to have d orbitals involved, so we're going to we're going to embellish this a bit. Okay.
Hey, I won't be doing this thing.
The symmetry part, I'm assuming nobody has ever seen before. Okay? It would not hurt you, if you've got the book, to read the book. If you have not read, if you do not have the book, go to YouTube and just plug in molecular symmetry and watch 5 minutes of it, or read 5 minutes of it, because it's going to be foreign. This is going to be something that you've never ever seen before.
And then something for next week.
You got all that.
Well, I'll be here from Wednesday. I'll be here Thursday.
Maybe.
Let it sink in.
I'm sorry.